In today's video, we are considering quantum algorithms. These are the main quantum algorithms available today. In the last video, we discussed one quantum algorithm, that was Grover's algorithm, that provides quadratic complexity gain over the classical algorithms. In today's algorithms, all the algorithms that we discuss provide exponential gain in complexity over the classical algorithms. And these, along with the Grover's algorithms, are major algorithms which are used in many different applications. And in fact, in the quantum computing two-part module of this course, we will be using these algorithms to use them on quantum machine learning to provide quantum machine learning algorithms. First algorithm we discuss is fast quantum algorithm. It's called quantum Fourier transform. Start with discrete Fourier transform. This is the transform which we all know. You take in time domain a signal x0, x1 to xn minus 1. It could be complex variables, and these are transformed in the transform domain, in the Fourier domain, to y0, y1 to yn minus 1, where yk is 1 by square root of m, sigma m is equal to 0 to minus 1, xm e raised to minus 2 pi ikm by n. The corresponding quantum Fourier transform is for the same size of input of length n. You make first orthogonal basis vector 0, 1 up to n minus 1. The interpretation of this is, suppose n is 4, then n minus 1 is 3, then this means that these are vectors 0, 0, 0, 1, 1, 0, 1, 1. And these will be in two-dimensional qubit space, and we know that these form orthonormal basis in that. For vector j in this, QFT of j is given by 1 by square root of sigma k square 0 to n minus 1 e raised to power 2 pi I j k by n, and we are taking vector k here. So if you see this definition, it's very close to DFT in classical domain. Now, once we have taken the QFT of any of these basis vectors, then we can easily find the quantum Fourier transform of any arbitrary vector. This is j square 0 to n minus 1 xj j. And of course, for it to be a state, mod of xj square summation over all j should be equal to 1. So this arbitrary vector, QFT of that can now be easily computed from there, because QFT is a linear mapping. So you put QFT here and you take it inside summation j square 0 n xj, then QFT of j. So this is how you will get the QFT of the whole thing. You can rearrange that in such a way to show that it can be written as sigma k is equal to 0 n minus 1 yk k, where yk is the same vector that we have seen here. So this is how we can define QFT of any arbitrary state in the quantum domain. Quantum circuit for this can be given by this. Here, the same vectors actually should be x0 to xn minus 1. So you feed in those vectors. So x1 is here. You feed into H Hadamard matrix, then to R2, R3, Rn minus 1, Rn, and then it goes out. X2 goes to H here through H, then R2 to n minus 1. Here it was Rn, here it is n minus 1. And in this case, the R2 is controlled by this. And similarly, R3 will be controlled by the circuit coming from X3. Rn minus 1 is controlled by Xn minus 1. And what are these Rs? Rs are rotations. So this will represent a controlled rotation controlled by x2, and rk in general given here is given by this matrix 1 0 0 it is equal to pi I divided by 2 raised to power k. So this is how we can show that at the output we get the QFT of the sequence x0 to xn minus 1. Complexity of this QFT with respect to FFT is as follows. The best classical FFT algorithm needs of the order of n log n gates. QFT requires of the order of log square n. So compared to this, you get an exponential speed up over the classical FFT given here. So we have to just make one comment here. What you get here is the QFT, but you cannot observe that just like that because this is in quantum state. And as we know that quantum states cannot be directly observed. However, you can make a good use of that going forward. And one important example is this algorithm where QFT is used to get the phase estimation. And what is this problem? Let U be a unitary operator. For unitary operators, their eigenvalues are always of this type, so that the mod of the eigenvalue is always 1. So for this unitary operator, phi may be an eigenvector, the corresponding eigenvalue given by e to the 2 pi I phi for some specific phi. So given U and given this eigenvector, we want to find out this eigenvalue and equivalently this phase phi. So the algorithm to do that is as follows. You start with a vector quantum state, phi is this phi, then tensored with 0 tensored n times. So n0 vectors, and this is the input to the circuit. Then on this circuit, you apply I tensored with H Hadamard transform tensored n times. So basically on each one of those zeros, you apply H. Then on the resulting state, you apply this vector. This is sigma x equal to 0 to n minus 1 ux. Ux is this u raised to power x. Remember, x are these binary vectors going from 0 to n minus 1. Tensored with x with conjugate of this. You apply this. Once you get this, you are basically getting a Fourier transform, quantum Fourier transform of what we want. So once you get this state, on this you apply inverse quantum Fourier transform on the first register, this register that we are talking about, and then do the measurement. You get the Fourier transform in these phases here. To get the accuracy of phi phase associated with the eigenvalue of psi, you may not be able to get completely accurate one for any finite number of digits. So if you want this accuracy larger than this number n, then the capital N, the number of bits that you need, is related to this n as n is equal to n plus log 2, 2 plus 1 by 2 pi, and this is the ceiling operator where you take this quantity, take the integer just larger than this quantity. Okay, and this we will get the phase phi with n bit precision and success probability greater than 1 minus epsilon, where epsilon is given here. So whatever success probability you want, whatever accuracy you want, you can take small n equal to this and use the above circuit, you can get that. Now this is when to this circuit you have input a eigenvector phi of u. If instead of inputting to this circuit, you input any state, any arbitrary state, then what happens? You can represent the state as a linear combination of Ci and Ui. Ui are the eigenvectors. Eigenvectors corresponding to U. And since U is a unitary operator, its eigenvectors can form the orthonormal basis in the space, and therefore any state can be represented as a linear combination of that. So if you input this to the quantum circuit that we have given above, then you can get at the output on measurement an approximation of the eigenvalue of Ui. So any one of Ui with probability mod Ci square. The Ci is given here. So this is how, feeding in any vector state at the output measurement, you can get eigenvalues of different eigenvectors of this, of U with probability Ci square. In this phase estimation, of course, we have used QFT. Actually, we used inverse QFT. And this algorithm, along with the QFT, is a basis of many, many other algorithms. In particular, the Shor's algorithm, the famous Shor's algorithm that we are going to discuss next, uses this phase estimation thing. Now, what is the Shor's algorithm? Shor's algorithm attacked a very, very serious problem in number theory. And what it is about, given any positive number, if you want to find its prime factorization, any number can be represented as prime factors, P1 raised to power A1, P2 raised to power A2, Pk raised to power AK, where Pi are distinct primes and Ai are positive integers. Could be, of course, some of them can be, of course, 0. Now, given a large number n, finding its prime factors is not, in principle, an easily computable thing. It's, in fact, intractable. No known efficient algorithms are available. Time complexity of getting the prime factorization above is O exponential log n raised to power 1 by 3. So roughly it is of the order of n. For given n, is of the computations required is of the order of n. Because, so if you take n large, you will really need a very large number of computation, and this fact has been used in cryptography. In fact, this most popular algorithm used in cryptography, one is RSA and its related algorithms. They use this fact that given a large n, you cannot easily find its prime factors. The Shor's algorithm, quantum algorithm, can actually compute these prime factors in time complexity of the order of log n square, log n, log n. So basically, here is the order of n, and here is the order of log n. So you get an exponential speed up. And this, because in cryptography, this fact was used that you can't get the prime factors easily. If you have the quantum computers large enough, you can do that very, very fast. And once you do that, we can break all the RSA and related cryptography schemes that are being used today. And this, of course, have very, very serious consequences. So now we explain what this Shor's algorithm is. You start with n, the prime factors of which you want to find out. If n is even, you divide by 2. And you keep dividing by 2 till you get an odd number. If this odd number is such that it is a power of 1 prime. So if n is equal to p raised to power k with some prime p, then also it's easy to get this factor. Okay, so no issues here as long as you do that. So don't consider that case. For that, classically, we have good algorithms. Now consider the case when n is odd. So you have repeatedly divided by 2 to get an odd. And there are at least 2 non-trivial prime factors. Otherwise, you don't need to go further. You can classically do it well. So for example, if n is 15, so n is odd and it has two prime factors, 3 and 5. So this classifies for finding the, for using the Shor algorithms further. Now choosing such an n, if a is less than n and greatest common divisor between a and n is 1, then the order of this, of a with respect to n, is the smallest integer such that a raised to power r mod n is equal to 1. Again, we take the example of n is equal to 15. Suppose a is 4, then a is less than n, and GCD of a and n is 1. You take 4 mod 15, that is 4. So it doesn't satisfy this. You take 4 square mod 15, that is equal to 1. Therefore, order R of A with respect to N is equal to 2. Now we are going to use this finding, for a given A and given N such that satisfies GCD equal to 1. We will, in our algorithm, need to find the order of A in this case. Again, there is no classically efficient algorithm available to find order A. And this is what we will use a quantum algorithm to get it. But for now, suppose we are able to get order R for A less than N with GCD A n is equal to 1. So we proceed further. We have this N. Randomly pick A between 2, 3, and up to N minus 1. So certainly A will be less than N. If GCD of A n is greater than 1, then this itself is a factor of N. So in this algorithm, initially what we are doing is we are trying to find some non-trivial factor of N. It could be prime, it may not be prime, right? So GCD of AN, if it is greater than 1, it gives a factor of N. We take that and then you divide by this, you get the other factors. So you are finding two non-trivial factors. If GCD of AN is equal to 1, we move further. Now you find order R. Remember, in this case, we found order R using the quantum algorithm that we are going to discuss later. Again, repeating that there is no efficient algorithm to find order R in the classical case. Now, if the order R is even, you take B is equal to A raised to R by 2. So this is even, so R by 2 will be integer. So you take that mod N. So then take B square. This will become A raised to R mod N. And we know that by the definition of order, A raised to R mod N is 1. So B square is equal to 1 mod N. This implies you take 1 on this side, you get B square minus 1 is equal to 0 mod N, which implies that B minus 1 into B plus 1 is equal to 0 mod N. This means that B minus 1 and B plus 1 are both factors of N. If GCD of B minus 1 N is greater than 1 or B plus 1 N is greater than 1, you pick one of those. Then they qualify as a non-trivial factor of N. You pick one of them, B minus 1 or B plus 1, whichever satisfies this. Now, this is if the order that we found is even. If order R is odd or GCD of this, both of them is 1, then you repeat it by taking a new randomly picked A between 2 to N and keep repeating it. Eventually, you will get a non-trivial factor. Now we talk about how to get the order R. As we mentioned that there is no classical algorithm efficient which can find order R. So we describe now the quantum case. There is a theorem which says that if you randomly pick samples K1 and K2 from 0 to R minus 1, these two factors randomly pick, set them K1 by R, K2 by R, this R, and remove the common terms, and you get C1 by R1 and C2 by R2. Then once you have done that, you define R equal to LCM, lowest common multiplier of R1 and R2. This quantity is equal to R. So once you got R1 and R2, take LCM will be equal to R with probability greater than equal to 6 by pi square. It's pretty high probability. If you didn't get R, because we can, once you get that, we can easily check whether it is an order or not. Then you repeat this process. You again randomly pick K1 and K2 from this and repeat it. And since every time this probability is high of success, so very soon you will get R. Now the question is, we don't know R. Then how do you randomly pick samples K1 and K2 from 0 to R minus 1? So this is an issue because I don't know R. So this is what we find out through the quantum algorithm as we describe now. So to find K1 and K2 randomly without knowing R as given above, this is the algorithm we use. If A is less than 1, GCD AN is equal to 1, which is the case we have been going further, you define a unitary operator UA for this given A, which maps vector X into AX mod N vector, this vector. And on this, we will apply quantum phase estimation algorithm that we have just described before this to get the order R, and we explain how we do that. So you start with this unitary operator and define vectors uk equal to 1 by square root of r, sigma is equal to 0 to r minus 1, it is power minus 2 pi I ks by r, vector a raised to power s, where s is this, mod n. You define uk. We can show that these vectors uk are eigenvectors of this operator that we just define UA with eigenvalue equal to 2 e raised to power 2 pi I k by r. K is the same k here. So, and k could be anything from 0 to r minus 1. So there are r such eigenvectors. So if we know this eigenvector uk, then from phase estimation, we can get estimate of k bar r. Right? But again, now the issue is this UK, in defining this, we are using this knowledge of R. And as of now, we don't know R, which is in fact what we want to find out. So going further, using this UK, now we can show that vector 1 is equal to 1 by square root of R, sigma k is equal to 0 to R minus 1 UK. This can be shown, and we will show it in one of the tutorials which we may attach with this module. Now, take this one and use on this eigenvalue estimator, the phase estimator algorithm. Remember, when we describe phase estimator algorithm and you feed in any state, then at the output, you will get the phase corresponding to the eigenvector of u with certain probabilities, right? So using that fact and putting this as the input to the eigenvalue estimator, or you can say the phase estimator, and then making the measurements, we get approximately k by r with probability 1 by r, because all these vectors, so one is given by this. So the probabilities corresponding to eigenvalues of this will be 1 by r. So this gives a uniform probability, one element k from 0 to r minus n, which is what we were looking for. And this we have been able to do it without knowing r, because we have fed in only one. And in the phase estimation hardware, we are going to use the knowledge of UA, which we know. Now, so you do this measurement once, you get 1 k by r, you do it second time, so that way you'll get k1 by r and k2 by r, and then you use the theorem given above to get the estimate of R. And you keep repeating it till you actually get it. So this is our Shor's algorithm to get, for a given n, two non-trivial factors. Remember, what we wanted is, for a given n, all is prime factors. Now you proceed further with that. Now you have got, for n, two non-trivial. Non-trivial means one is also a factor and n is also a factor. We are not talking of 1 and n, some non-trivial in between. Once you got those two factors, you can easily check whether those are, or any one of them, is a prime number or not. If any one of them is not a prime number, then you run the same algorithm using that as n and get two more non-trivial factors of that. You keep doing it. Eventually, for each one of them, which is factors you have found, if any one of them is not a prime, eventually by repeatedly doing it, you'll get the prime factors. Next algorithm is HHL algorithm. This is Haro-Hassidim-Lloyd algorithms. This came up much later than the previous algorithm that we have given today. Even the Grover's algorithm. All those algorithms were invented by 2000. This algorithm came in 2010. Now, what is this about? You want to solve this linear system of equation Ax is equal to B. A and B are given to you. A is a Hermitian vector matrix, n by n. A and B are given. We want to find out x. So this is simply solving a system of linear equations. Of course, we have algorithm available, classical algorithm, and you can call them efficient algorithm because they are not like, they don't require exponential number of computations to solve it. However, this is a very important problem. We use it all the time, everywhere. And the quantum algorithm we are going to do it actually gives an exponential gain in complexity compared to the best classical algorithms we have available to us. So we are assuming right now A is Hermitian, but this assumption can also be removed and it will work for any general n cross n. So start with A Hermitian. First thing we do is we prepare a state 0, B, 0 vectors. B is same B here. Now apply on this phase estimation on the last two registers. So these are the last two registers. On this, we apply the phase estimation algorithm, and by applying that, you get the state sigma j, beta j, O, lambda j, uj, where lambda j are the eigenvalues of A and the corresponding eigenvectors are uj, and beta j are these coefficients, where B, this B, is written as summation of beta j uj. Uj again are the eigenvectors of this. Why we can write any B in this form is because A is Hermitian matrix. If A is a Hermitian matrix, then we can find eigenvectors of A which form a orthonormal basis in this space. Therefore, any vector B can be represented in this form. So starting here, applying phase estimation on these two registers, we get this state. Next, we apply controlled rotation. This is e raised to a minus iy, rotation by y, theta, on the first qubit, 0. So this is the first qubit here. Apply on this. E raised to power control rotation by e raised to power minus iy theta, where theta is given by sine theta is equal to c by lambda j tilde. We are writing as lambda j tilde, but because this is an approximation of lambda j we get from the phase estimation algorithm. Remember, phase estimation algorithm gives an approximation of the actual lambdas there. And c is some constant not equal to 0, which we a priori fix. So this is the next step. After that, we apply inverse phase estimation on the last two registers to disassemble the eigenvalue register. After that, you make measurement on the first qubit. If the output is 1, then the last register. So the last register here will have a state x where ax is equal to b. So this state contains the solution x that we are looking for. So with this, we end today's video. Today, we have explained several very important quantum algorithms, and an important feature of all of them is that they provide exponential speed up over the best possible classical algorithms. And these are very, very important algorithms which are being used and exploited today in a very important application of machine learning, and machine learning algorithms are being speeded up via these quantum algorithms to gain substantial gains. And it is a very, very important algorithm because machine learning AI is being used everywhere, and their data and the dimension can be huge. And for example, in ChatGPT, to get the ChatGPT, the huge amount of computations have been used. If you use the quantum algorithms, then we can have a substantial gain in power as well as in time. Of course, we need to have a large dimensional quantum computers, but they are coming very soon. And so therefore, we expect that soon these algorithms will be very useful in this very application as well, in addition to other algorithms. Thank you very much.